Okay, thank you to joining this virtual edition about about the user on the user conference about JMAG and pacing. Today the topic is about using Cradle CFD and JMAG on in electric motor for better handling thermal challenge. So the presentation will be done by Elia Cipolato. So Elia Cipolato is coming from Hexagon MSS software from in Italia. He worked actually as a CFD project manager, coordinating and managing all the activity covered by a CFD in the Italia region. So and also by using and distributing Cradle's CFD tool. So Cradle, it is official smart solution for computational thermofluid dynamic developed by Hexagon MSA software company. So since he master's degree, so he got several more knowledge and experience in CFD because he developed, for example, his master's thesis at the Rolls-Royce Power System in Germany, where he used CFD, where he built or developed CFD simulation. So he also worked for Enginesoft. So Enginesoft in Italy with an official ANSYS reseller. So he worked as a CFD project engineer, where he tried to apply the CFD simulation in different application area. So from automotive area, aerospace area, and so on. So earlier we have around 30 minutes of presentation. Then after his presentation, we will try to answer your different questions. So feel free to type all your question into the chat box that you have into Zoom's of Wova application. And so welcome, Ilya. So now you can start your presentation.
Okay, thank you very much, Didier, for your introduction. I hope everybody can see my screen. Okay, as Didier said, I work in Italy as a project manager for Hexagon MSC software, and I'm specialized for computational fluid dynamics, which is in MSC software actually done by Cradle CFD software. So the title of the presentation of today is Using Cradle, CFD, and JMAG in emotors for better handling on thermal challenges. What will be this presentation about? So let's start from just a short introduction. Electronic devices and equipment are virtually tied up in every aspect of our life. So while every increase in consumer demands are driving the sophistication and complexity of electronic products available in the market, electronic devices are also becoming highly compact. So engineers are now faced with challenges of tightly packed components constituting geometrically complex heat flow paths, posing strong need for advanced thermal analysis to develop products that do not heat quickly. CFD in this case plays a crucial role in assessing product performance early in the design phase. The efficiency of electronic components and the product life of the devices are dependent on the heating and the ability to control the temperature through sophisticated and intelligent cooling mechanism. With the help of CFD simulation tools, an engineer can locate hotspots and quickly modify the design of reposition components, change fans, replace heat sinks or add vents, etc., to enhance the product design before it's even put into production, so saving a lot of time and money. First of all, MSC software has a long-term experience in simulation performed at different levels and in multiphysics. Starting from well-known solutions as MSC Nastran, for example, for structural analysis, through all its life, MSC software gained experience also in different simulation fields, as multi-body dynamics with Adams, nonlinear structure with Mark, manufacturing and metal forming with Simofact, acoustic with Actron, gears and bearing system with Romax, and last but not least, Cradle for computational fluid analysis, or CFD, which is a product we will talk about today. Okay, so first of all, what is Cradle CFD? Cradle CFD has not only to be intended as a single product, but it has to be considered as a solution for general CFD, which is composed by different solvers and tools. Cradle CFD solvers use finite volumes method as a solution method, which is a well-known methodology, which is very suitable for computational fluid dynamics. This method allows also an accurate representation of fluid dynamics phenomena, and so it's suitable for a large number of applications. Basically, every time you have a flow field, heat exchange, turbulence, and many other models are involved, Cradle CFD can be employed. Cradle CFD solution actually consists of two main solvers, which are now explained. SC string, which is the first one, that, as you can already see from the picture, is a structured mesh solver. That means that the fluid domain is discretized through a regular hexahedral mesh. This allows SC string to be very fast in calculation time with low CPU and memory consumption, especially if compared to common CFD solvers, and can be more suitable for applications with low complexity geometry, as for electronic simulation, for example, and large scale models, as for architecture. Instead, SCFlow, which will be actually the product we will be talking about today, different from the previous one, SCFlow uses as an unstructured mesh to compute equations through the domain. The use of unstructured mesh allows more general compatibility, different from XStream, with complex geometries and shapes, and makes it more suitable for almost every kind of simulation. So every time you have a geometry of every kind, of different kind, you can simulate it with SCFlow without any kind of problem. You will be sure that the polyhedral mesh will replicate the geometry very strictly, and you will have, as a result, a very realistic simulation. And the last, but on the workflow process of CFD, there's SC Post, which is, as the name says, it's a post-processing tool which comes with both of the softwares, and comes every time inside Cradle CFD softwares, and it's a very powerful results visualization software, so that you can post-process your results and take your and make your evaluations. Cradle CFD softwares then can be applied to many different application fields, from aerospace and defense, automotive, through chemical processing and oil and gas, architecture, consumer goods, electronics, as well as heavy manufacturing and power generation. As we said, the kind of solution methodology implemented in Cradle CFD solvers allow the solution every time a fluid flow and thermal phenomena are involved. Today, we will talk more extensively about SCFlow, since it represents the optimal solution for the fluid dynamics and thermal analysis of emotors. So now, let's for a moment forget about CFD and let's talk about e-mobility. We already know that how large is nowadays the e-mobility business. I just would like to stress some key numbers to highlight the size of the market we are talking about. In particular, we can see that the market size in the order of magnitude of $100 billion, with an expected growth of 28% for automotive e-motors. If we look at the market share by application, we can see that e-motors are not only used in motor vehicles. Of course, it's a large part, and it's a part that is growing faster than the others, but many things we are discussing today in this session will also be valid for e-motors used in machinery, for example, HVAC, and home appliances. So even in this let's say, narrow discussion, we can expand these evaluations for a lot of different application fields. And if we look specifically at the motors for the automotive industry, we can see different actors playing a major role on the market. Some OEMs are working themselves on the development of electric motors. It's interesting to note that many of these companies are already equipped with our simulation tools, and we know that some of them are not using them just for this specific application. And finally, some suppliers and OEM are now creating joint ventures specifically for developing e-motors. As an example, a recent joint venture was between LG and Magni International. And if we step away from automotive for a second, we can see that there are also many very large actors in all regions developing motors for a large variety of applications. For these companies, the priority may be slightly different. For example, more focus on durability and less focus on noise and vice versa. But again, our solutions can be absolutely support their activities. So let's go back to the point and to some more technical discussion. And let's talk about first e-motor design and optimization. This is the main challenge we are helping our customers solve. Every time we talk about optimization, we have to determine what are the different objectives, constraints, and parameters. As far as the objectives are concerned, e-motor designers will have to balance different performance aspects such as efficiency, which is very important. Which is very important in range, which is the #1 problem. Having a great battery system, but in an efficient motor is not going to help us much. Noise and vibration, and we will see just later why. Thermal performances, since we don't want to have to stop our motor to let it cool down. And finally, durability, which is always a very important concern about reliability of our vehicle. The constraints will be around development and production cost, basically, development time, packaging, and manufacturing. And finally, the parameters we will work on will be the electronic and the electromagnetics design. There are different architectures available, and each architecture has a lot of parameters we can act on to change the behavior of the system. Geometry and materials. Here is worth mentioning that the geometrical changes may be quite large. For example, when we change parts of the housing, but they can also be extremely small changes, since some slight changes in the rotor and in the stator geometry can completely change the behavior of our system. Another parameter is sure cooling strategy and motor casing and covers. We will now enter in a more technical discussion that begins by talking about the thermal issues that e-motors face during their operation. So, probably you're going to say something like, rotating electric machines exist since 1834, so why do we need to improve now something that has been existing for decades? So the answer is that the main difference with the previous industrial applications is that an electric vehicle needs to work under very severe variation speed and load conditions. So what we want is, at the end, to avoid overheating, as it could lead to breakdown of the stator winding insulation or demagnetization of the magnets. In addition to these above-mentioned issues, we want obviously to improve efficiency under normal conditions. That means we need to have the most predictable thermal behavior of the components to finally design the most appropriate cooling system. We can easily understand that the thermal management is then critical to improve electric machine performance and ensure reliability. So where does heat comes from in an e-motor? Heat can be in general generated by different types of losses. First, we will have electrical losses and electromagnetic losses and mechanical losses. The first two ones are usually calculated by electromagnetic softwares like JMAG, for example, which we will soon see in this presentation. On the mechanical aspect, instead, friction in the bearing is calculated, for example, by Romax, which is another software of the MSC family. Also, there will be windage losses that has to be taken into account, and this can be easily calculated inside Cradle SC-Flow. So, as far as we saw, we can consider these losses as thermal sources in the system. And how do we integrate these thermal sources into the system thermal calculation process? Here we have different choices, depending also on the level of accuracy we want our final model to have. As first example, one first simple choice is that we read the joule losses directly in SC-Flow by reading a CSV file generated by electromagnetic calculation, for example, performed in JMAG. If instead we want to be even more accurate, we can also integrate in the process the mechanical losses by adding them after a calculation in the rotating parts made inside, for example, ROMAX software. Either ways, the final step will be always adding all these sources of information inside Cradle SCFlow for the final thermal and fluid dynamic simulation. We'll see more in detail in the next slide how this works. But first, let's make another consideration, which is actually the cooling of the system, because we are actually producing a lot of heat, and we need actually to put away this heat. We need to cool the system down. So there are different types of cooling systems. The first one, probably the simplest one, is air cooling, because no fluid is involved. Air cooling provides low pressure losses, but it's not suitable for all systems, since the cooling performance is quite poor if compared, for example, to other solutions. Moreover, you need to efficiently shape the fan, for example, that is performing the air cooling, and because the fan shape can modify the cooling performance a lot. A second choice would be for example, we enter in the liquid cooling methodologies with water, for example, or monoethylene glycol. And this can be considered as a good compromise between pressure losses and cooling performance. Oil cooling is another kind of cooling system preferred for some solutions, since it provides up to 15% more of cooling efficiency than water cooling. According to the AV architecture, if the electric drive is included inside the gearbox, different types of cooling systems can be investigated. And of course, for each system, Cradle will be able to run different types of thermal or fluid analysis or fluid analysis. Okay, yeah, so obviously for each of these systems, there will be a different fluid dynamic analysis, but the important thing is to consider is that inside SCFlow, we can perform all of this kind of analysis involving all of these components. So apart from what we already said, we need also to consider that the needs of the market, especially for e-motors. The main requirement today is obviously to reduce the overall weight of the electric motor, ensuring at the same time a good thermal management. And unfortunately, these two aspects, they go one against the other, because by reducing weights, so reducing sizes and tightening everything together, there will be actually less space for heat to be taken away. So the thermal management becomes a very huge challenge. The idea is to reduce the energy required by any motor so as to extend the AV range. As we can see, all these aspects are strongly connected to each other, since downsizing the motors will require very effective thermal management. Cradle CFD is able to accurately predict the heat distribution inside the e-motor, but as well as the thermal resistance of the air gap flow according to the rotational speed. And those analyses will be helpful to improve cooling efficiency. Let's now focus about SCFlow. As we said, SCFlow is a general purpose CFD software that fits perfectly the needs for e-motor simulation. A key feature for this kind of software is for sure its ability to be interfaced with other softwares solving different physics and disciplines. Thanks to our interface openness, we will be able to read data from external software like electromagnetic ones, and by tackling multiphysics by using MSE1 portfolio, so that we'll be able to offer a very accurate and realistic model. SCFlow has a lot of key features, but some in particular are exactly what's needed for e-motor simulation. E-motors are very complex machines made of a lot of different components with a lot of details that must be considered in order to provide a more accurate and realistic simulation. SCFlow uses by default the polyhedra type mesh for domain discretization, which is very accurate and suitable for most applications. However, sometimes this kind of discretization can become tricky when the system has a lot of different components with a lot of small details to replicate. In this case, a large amount of human time would be required just to proceed in CAD geometry defeaturing and simplification, and to prepare actually the geometry for an efficient meshing process. For this reason, SCFlow has been equipped with also an alternative meshing process made specifically for these applications, which is voxel fitting meshing. Voxel fitting meshing is a discretization methodology in which the volume mesh is generated directly from the CAD data, without building the analysis model and generating surface mesh. This is a very important aspect, since it's possible in this way to generate the calculation mesh even if the parts interfere with each other and have some tangential contacts. As a result, hexaedral dominant polyhedral mesh is generated. And the good point is that inserting boundary layer modeling is also possible, so that we can be more precise even for near wall treatment. This method is then very suitable for emotors, since there's no more the need to spend hours and hours of the featuring time. We just give the CAD to SCFlow and he will do the work for us. That's how simple it is. Let's then proceed with another SCFlow feature which can be suitable for emotor analysis, especially concerning the oil cooling analysis. As we saw before, there are different ways to cool down an electrical motor. One of these is oil cooling. Through a detailed fluid material specification, SCFlow can model precisely any kind of fluid material and predict its behavior inside the simulation process. As an example, oils can sometimes have variable behavior when flowing, for example, at different temperatures, or if they are subjected to strong tangential forces, for example. And that's because in these cases, we have significant changes in their viscosity. SCFlow can take into account these aspects by defining, for example, variable viscosity property. And this can be done in many different ways, such as inserting tables, inserting user-defined functions, and inserting scripts, for example. Again, for liquid cooling, and this is true also for water cooling, SCFlow inside has built-in a cavitation model, which is also a very key feature to take into account to assess if our machine in some parts has some cavitation problems in order to avoid some erosion problems and also some bad heat removal efficiency process. Another strong feature is for sure the visualization that is possible through many different tools. In fact, a good simulation would be useless without an efficient results visualization. Before we saw SCPost, and which is the main tool we can have to have, for example, a qualitative results evaluation. For example, we can see thermal maps, pressure losses, flow behavior, and we can map these results as an input for further analysis or apply model reduction, example for 1D analysis. Another great tool that comes with SCFlow and in general that comes with Cradle softwares is for sure heat path view, which we will see in the next slide. So heat path view is a very small but very useful tool that allows us to see all at a glance all the thermal information regarding our system. For example, we can see characteristic temperatures in all our components. So we will have in the setup, we will have, when we import the model in the pre-processing, we will have a list of components that we decide, we name them, we save our regions, our locations, and then we will have all these locations and these regions and these components for the whole process, included heat path view. So here you can see then all the characteristics like temperatures in all the components we have, thermal fluxes between them, and also heat path view can distinguish and can give us the contribution of every different kind of heat transfer inside the system. Like it says actually, which is the part that is exchanged by convection, for example, the part that is exchanged by conduction, and the part, if present, that is exchanged, for example, by radiation. And also this very useful tool is giving us a sort of map that shows us which are the preferential paths of our of the heat exchange inside our system. reporting also heat fluxes, thermal resistances throughout the whole system. And so finally, you can get the results all at a glance by using a simple tool, which is a real differentiator on the market. This little tool helps designers not only to visualize, but to analyze all heat dissipation inside their models. And they will be then focalize their attention on the true problems and will converge very quickly to a better solution. As we said before, SCFlow alone won't be able to solve the entire process of simulation of an electric motor, since this kind of simulation involves different types of physics and disciplines. That's why it's crucial to develop as much as possible interfaces with other softwares, providing a solution to physics other than fluid dynamics and heat exchange. Luckily, MSc software has in-house almost everything it takes to make a complete simulation, apart obviously from the electromagnetic ones. Regarding MSc product, sorry. For the reason you just see, a crucial step in MSc software has been the development of a tool that could make a connection between different physics. That is MSc COSIM engine. What does this actually mean? So, as we have different software, for example, Mark and Nastran for structural analysis, Cradle SCFlow for fluid dynamics, Adams for multi-body dynamics, and Ectran for acoustics. The obvious decision was to build a way to connect all these instruments in order to have a multidisciplinary simulation. In particular, we can do fluid structure interaction, fluid multibody interaction, and now fluid structural and multibody interaction. Obviously, when a transiency of the analysis is done, and not only transient actually, there can be always the chance to perform also an acoustic simulation. So we can perform what is the so-called aeroacoustic simulation. And this is another very important aspect in emotors development, since electric vehicles are actually much more silent than the combustion engines ones. So we need to reduce the noises as much as possible. Obviously, for physics that are not covered by MSc software, an openness with other software is surely possible. One strong connection for electromagnetic simulation is for sure the interface with JMAG software. Once the electromagnetic simulations is accurately performed inside JMAG, motor losses data can be easily exported into CSV or Nastran BDF file format. These formats are natively read by SCFlow, so then these exported files can be imported and mapped into the heat sources condition and used as the inputs for the thermal analysis performed in SCFlow. This is actually what the process looks like. So we want to perform an electric motor simulation, and JMAG actually performs all the electromagnetic simulation. Then it calculates what are the losses, both Joule iron losses and electromagnetic forces. And then the results can be imported both in MSc Cradle, for example, for thermal fluid dynamic simulation, and also in MSc Ectran for acoustic noise simulation. And how technically this is done? This is done through this process. So inside JMAG, you create the magnetic field analysis model, then you run the analysis, and you then confirm the result distributions in terms of Joule loss densities, iron loss densities, electromagnetic nodal forces, and then as a post-processing, you export density distribution map using this tool, which is the multipurpose file export tool. With the help of this tool, we can export the results in BDF, as we said, or CSV file, and in particular, the Joule iron losses result data can be read by Cradle SCFlow, and then SCFlow gives as a result the thermal map heat distribution, and from actually a fluid dynamics thermal model. Instead, with electromagnetic forces, we can map them inside MSC Actran or Romax, and by mapping the nodal force distribution to the load condition from noise vibration model. So we can see this process is actually quite easy and straightforward to go directly to the point and having a complete simulation. On the market, we are seeing as well as commercial electrical vehicles, which are using extensively start and stop actions. As duty cycle influences the lifetime of e-motors, it is important to integrate this aspect inside the thermal analysis. Heat is transferred then from coil to the magnet. With Cradle, we can observe the evolution of temperature produced by the e-motor losses, accounting for pulse width modulation, drive losses. So we can see that by coupling these different softwares together, we can have all the informations exchanged, and as a result, we will have the resulting thermal behavior of our system. And yeah, in an ideal working operation of diesel electrical motors, if we define the temperature gain by the multiplication of the thermal loss and thermal resistance, obviously we will have good performances when we can lower Q, so the losses, and the thermal resistance. By modeling in the exact ways the losses and the thermal resistances give us a very realistic simulation. And then obviously we already talked about the losses we can have in our system, and the losses actually can be calculated by different softwares depending on the physics we are evaluating. So copper loss, for example, calculate the heat generated by the electrical resistance of windings and is predictable with JMAG. Iron loss, so we can consider the hysteresis loss and the eddy current loss, and both of them are predictable with JMAG. Instead, the mechanical friction, but more importantly, the wind loss, so it's actually like the fluid friction loss can be predicted by SC flow. So once again, if we combine all these softwares together, we will have all the instruments to make an accurate and realistic analysis. I speed a little bit up because I see the times is quite up. So okay. Yes, it's actually what we already saw. So you can see that inside the CFD analysis, you can model very small and thin gaps. Actually, this is a zoom, but we are talking about millimeters or even less. And so we can calculate all accurately all the distributions of the fluid flow inside these small cavities and evaluate in a very accurate way all the windage losses. And so we can also have a help to model the animation, the motor in a very accurate way, in a very efficient way, most of all. And in the same simulation, we can also include, as you can see in this animation, the cooling of the system by, for example, a liquid-cooled circuit which goes around all the electric vehicle. Then another challenge that leads always to a very complex thermal management is the fact that the electric motor, it's not just the electric motors involved, but there's also all the systems that are required to run efficiently the electric motors and to connect the batteries to the traction system. And example, as the inverter is. So this is another component that actually dissipates a lot of heat, but for reasons of space, actually, we need to compact all these components together. And so we can easily understand how the thermal management is very, very important to efficiently run these machines. So if you want to, if if you want to leave you with some key takeaways, keep in mind that our solution provides time development and cost saving, leading to a better productivity and optimizing emotors for multiple disciplines. This technology provides answers to non-expert people who need very easy to use products, up to the gurus who need very accurate solution. MSC1 is a killing solution providing multiple physics, and last but not least, our products are very open to interface and to integrate to the mobility ecosystem. Last but not least, actually, our openness, SC Flow openness, actually with JMAG for all the electromagnetic part. So, thank you for the attention, and hope there's still some time for a Q&A session.
Okay, thank you, Mr. Elliot. Thank you for this good presentation. So for the moment, there is no question, but feel free to type your question into the chat box of Zoom or Wova application so that we can answer your question. I got one question. Is it possible to export the mesh and the heat flux density coefficient?
Yes, absolutely. With the SC Post, there is a feature which allows you to actually import, for example, the coordinates of another mesh. So let's make an example. You want to perform a thermal structural analysis. Okay. Then you make the CFD analysis. You have the thermal results. You have the thermal maps on the CFD mesh. Then inside SC Post, you can import the coordinates as a simple CSV file of your structural mesh with all the coordinates of your structural nodes. Then in SC Post, you can map the CFD, the thermal results into the coordinates of the structural mesh. And then from SC Post, you can export again this information in order to use it, for example, as an input for a further structural analysis. And so you obtain actually a thermal structural analysis. But in general, the answer is yes.
Thank you. Thank you for that. I think there's no question, but you can also contact the support of JMAG or Cradle if you have any question on Cradle or JMAG. So thank you for joining this presentation. I think the next section of
Thank you for attending.
Yes, the next session of the presentation will be this afternoon, starting at 2 p.m. So you will have the first presentation will be about the feature of power electronic control using PSIM software. So feel free to join this presentation using the same interface of Wova. So you just need to update the interface, then you go to the agenda and the section, then you will see this this presentation. Thank you for joining this presentation and have a good day. Thank you and bye.